Alright, so we're going to look at the conical pendulum, and we're going to derive some particular problems, or some particular expressions, okay? So a conical pendulum, first of all, has a common point in which something is perhaps hanging from it, usually by a string or something similar to that, and it's swinging back and forth. In this case, it's spinning, or it's twirling around in a circle. And it's creating a cone shape because it creates this nice horizontal circle at the bottom. And the string, that the tensional force, is causing the rest of the cone. It meets up here at what's called the apex. Okay. And so we'll look at this and we'll derive some of these equations, and we'll also talk about why we know that if there is a gravitational force and you're spinning something around horizontally in the air, it is impossible for it to be perfectly horizontal without some additional force. Okay. So anyway, so what we need to find is an expression for the linear speed, the tangential speed of the object, the tensional force provided by this string right here, the period of rotation, how long it takes it to spin around in one full rotation, and the centripetal acceleration, which of course should be proportional, inversely proportional, to the force of tension by force of the mass. So we can find force of tension, we can find centripetal acceleration pretty easily. And the capital T here is implying that it's the period. Now, write these in terms of what? We don't have any numbers. I'm going to write them in terms of the mass of the object. So in this case, this little plane thingy spinning around, the length of the string, the radius of the circle, and it says in terms of phi, the angle to the vertical. Well, it turns out I only need two of these. You can just use trig to find the other one if you really needed to. I either need the length of the string and the radius, or both of these lengths, or I need one of the lengths and the angle. You don't need all of them. But in this case, and it's a little overkill, I'm going to rate everything in terms of radius and phi, if possible. So let's start by drawing a force diagram. What do we know? We know a lot, hopefully. Hopefully, anyway. So we do have force of gravity, pulling this guy down, and you have force of tension. Unless this is some magical plane that actually flies, it does not have lift. This is probably say no lift. Let's say this is our force of tension right here. And there might be drag forces, but those act opposite in motion, so it would be coming in and out of the plane, depending on the motion of the object. Let me say this is spinning around this way, though. It's completely irrelevant. It doesn't matter. I'm going to find the magnitude of the velocity, the linear speed. Alright, so let's identify where the centripetal acceleration direction is, because that's important. If the object is right here, centripetal acceleration is in this direction, towards the left. So let me make a centripetal axis, because that is always very important. Here's my centripetal axis. So we normally call our x-axis for the kinds of problems that we do, the centripetal axis, which means our y-axis must be vertical to that. It must be perpendicular. Just a little bit to the left of gravity, so you can or right to gravity. So you can see that. And then, of course, we're going to sum up all of our forces. Wrong color. We're going to sum up the forces in our centripetal direction. And we are going to sum up the forces, and I put this over here, in our y direction, calling y the vertical. Sorry, too much golden. Alright, so in order to do this, and by the way, when we're done with the centripetal one, this would equal mass times the centripetal acceleration. Whereas in the y direction, if this truly is spinning in a horizontal circle, it should not be oscillating up and down. It should be spinning in a nice horizontal circle, not moving up or down. So it should not be accelerating in the y direction. So some of these forces should equal 0. Okay, so in order to work this out, we're going to need to figure out where phi is relative to this problem. Now, we need to identify also where the centripetal forces are. Notice their gravity is all in the y direction. So it has to be over here for this, the force of tension. And if you look at this component with my horribly non-straight line, this right here is the centripetal component of the force of tension. This component right here is what's keeping this in this horizontal circle. And then, so let's figure out, is it sine or cosine? Well, if this is theta, it's going to be 90 minus theta. So this one will be, or excuse me, phi. This one will be phi. So this part right here is ft sine phi. So the sum of their forces in the centripetal direction, the positive is pointing towards the center. So it's be ft sine phi. And that should equal the mass of the object times the centripetal acceleration, which I don't feel like filling in right now. Well, I know what sine of phi is, I know what the mass is, but this is going to be phi squared, which I don't know, and I need to find that. So there's just too many unknowns here. Okay, so now let's sum up the forces in the y direction. Well, if this is phi and this is force of tension, this would be ft. There is a force here, opposite the direction of gravity. This would be ft times cosine. So if we sum up our forces, I'm just going to say up is positive. In the y direction, we ft sine of phi. Excuse me, cosine. Erase that right off. Ft cosine of phi minus the force of gravity equals 0. And let's plug that in. And this is nice because I'm going to bring force of gravity over, which I know is actually equal to mass times gravity. And look at that. I know mass of the bob. We're saying we weighed it. I know gravity, and I know what phi is. And so now I have my first expression. Force of tension is equal to mass gravity over cosine. Isn't that nice? Let me write that up here. Keep track of what we got. Wow, we've got 1 out of 4. Great job. What I do notice is when I wrote up an expression for the centripetal force, or yes, the sum of the centripetal force, excuse me, I needed force of tension or something else to solve in here. So now I've got force of tension. So let's write that. Substitute that in. Mg over cosine phi times sine of phi. And let's say I want to solve for centripetal acceleration now. Well, you should notice there's a mass on both sides that cancel. You should notice something else. Something very mathematical about sine over cosine. It's tangent. So I have gravity times tangent phi is equal to the centripetal acceleration. So that's our second formula. Yay, our second expression. It's kind of interesting, too. The centripetal acceleration is really only dependent upon the angle and gravity. It's pretty neat. So that's going to be g times g times tangent phi. Alright, and then I know this should also equal centripetal acceleration is mv squared over r. So our m is going to come back into play. Oh, excuse me, not m. V squared over r. Excuse me. Our m is not going to come back in. So we can solve for velocity now, because that's something I didn't know, and I do know the radius of the object. So we're going to multiply both sides by r and then square root it. So there's our third equation. R, the radius, times gravity times tangent phi. Should give you the linear speed of this object. So rg tan phi. Can make a wrap on that. And lastly, how do I find the period of the function? Now, the period is how long it takes to complete one full circle. But it's also just the circumference divided by the velocity. Okay, because remember, it's like distance equals rate times time, and all the whole circumference is 2 pi r. And we know the velocity is rg tan phi. And I suppose you could simplify this, but I mean, really, that's all you need to do. So look at that. And let's make sure our units cancel. This is meters. It's going to be square root of meters. This is meters per second squared. So you get your seconds here. Anyway, so it's going to work out rather nicely. um, yeah, so because you're going to end up with a meter squared, and those cancel, and so your meters then cancel, and that's the period, and that's the last one. Oh. So you can find all these. It's kind of neat that you can find all these. So this was 2 pi times the radius over square root of RGT. Now, let's talk about how this tells us that we know it first cannot be completely horizontal. Um, so I'm going to look at a new page real quick, and if it was completely horizontal, that is the wrong line I just drew. If we look at the force diagram, this would be your centripetal acceleration. You've got gravity. This would be your force that's pulling it in. This would be your tensional force. Imagine you're swinging something over your head, and you're saying, oh, it's perfectly horizontal above my head. And this is gravity. So that means it has to be falling because you've got an acceleration pulling it down in the y direction. This would be this would be contributing to your centripetal force, sure. But what about here? There's got to be something to compensate it. So therefore, that angle between the vertical and the tensional force, it can't be 90. That angle between the horizontal and force of tension cannot be 0. It has to be vertical. And if we look here at what this conical pendulum was, what happens? Let's look at the force of tension, for instance. What if phi right here was actually 0? Okay, so or yes, so what if phi was 0? So this angle is completely. I'm sorry. What if phi was 90? That's what we should look at. If phi is 90, then this will be completely horizontal. Okay, and the force of tension will be like this. So if phi is 90, what's cosine of 90? Well, cosine of 90 is 0, and now you have an undefined expression. So phi has to be less than 90 and greater than 0. It cannot be 0. As well, because now that would be vertical, and I mean, it's just not a pendulum anymore. It's not spinning around. So that's very important. And we can back that up with the mathematics, and you can also back that up with just common sense with the force diagram. And that's it.